Okay, so optimization. What is optimization all about? Strongly, you guys are big boys and girls. I'm not going to force you to do this, but I would strongly encourage you to just really tie into this as much as you can today, because there's a lot of things to consider. So optimization, think what that means. If you want to optimize something in life, what are you typically trying to do? Make it better. So if you're trying to optimize the settings for some type of a device, you're trying to find the settings that are going to make it perform the best, right? So most efficiently in most cases, right? So we're trying to optimize always implies that you're minimizing or maximizing some quantity, whichever is going to make things better, right? Or is going to accomplish the goal that you're trying to accomplish. So right away, you can probably start to establish, just conceptually, there's going to be a tie to the stuff we've been doing. Think about all the work we've done with tables, right? Which, when I say work with tables, that's like an umbrella that includes increasing, decreasing functions, finding extrema, right? Finding inflection points, finding upward and downward concavities. Well, for optimization, the part that we're really focusing on out of those tables is we're trying to find extrema, right? Minima and maxima, okay? And so we're gonna take. I love this part because it's an application. It's a really powerful application of the math we've been talking about. The problems aren't going to be, the math that you're going to find is not going to be that hard. I mean, we've done the hardest math problems that we're going to do all year in terms of doing the differential calculus on taking derivatives and, I gave you lots of purely mathematical problems that are hard to do, but oftentimes the problems that you get for real world examples are modeled by easier things like polynomials, right? So a lot of times the math part's not going to be as hard, but now the challenge is to make the connection between the physical application or the geometric application or the economic application and the math we've been doing, right? So let's take a look here. Let's just consider this problem, and then let's sort of talk our way through an approach to this, and then we can kind of try to articulate or enumerate an approach, and what we'll come up with is the standard approach, and then I'll give you the handout, and you kind of get almost a recipe to follow, a procedure to follow whenever you're doing optimization problems. In future years, in math, for those of you that are going to go on and do higher level calculus stuff and differential equations, you'll do the same kind of stuff, but it'll be the same process, but you might be looking at differentiating with respect to more than one variable. So there are going to be some extra dimensions, in mathematically and in terms of just the different types of things you can do. So the word could be either metaphorical or directly applied mathematically, but there's going to be extra stuff you're going to add to more complex problems in the future, but the process will remain the same for optimizing, okay? So a manufacturer wants to design an open box having a square base and a surface area. Let's just do it smaller so we can see it. And a surface area of 108 square inches, as shown in figure 3.53. Well, that's figure 3.53, I guess. What dimensions will produce a box with maximum volume? So that's our goal, right? We've only got so much cardboard to work with per box, for whatever reason. Maybe it's a weight reason, who knows? But we want to maximize the volume for these boxes. Okay, so we want to be able to come up with, we want to relate this to the stuff we've been doing. Think about the kinds of things we've been doing, the kinds of problems we've been doing. Have always been things like, you've got some function, maybe it's, who knows, x squared minus 6x minus, what's it going to be, minus 40, right, is your function. And you want to try to find all relative extrema or something, right? We've always done calculus on functions that only have one variable, right? In fact, this class could probably most appropriately be called, and I think I've even said this before, calculus of a single variable, right? Or single variable calculus. That's what first year calculus is. So obviously when we're doing problems, if we want to be able to leverage all the stuff we've learned, we want to be able to always take these kind of applied problems, and somehow we've got to be able to write these as functions of a single variable, right? So we always kind of have to have that in the back of our mind as we're approaching this. But we want to just come up with some kind of a function here on some kind of a domain that makes sense for this physical application, and then we want to find a relative maximum, or an absolute maximum for that case, right, for that matter, for whatever quantity it is we're trying to maximize, which would be volume in this case, right? So we should expect that somewhere down the line on this problem, we should be able to get v of x equals some function over some domain that makes sense mathematically and physically, and then we'll just make a table that reflects that domain and find the absolute maximum on our domain. Just that simple, right? Yes, sir.
So is this similar to like the beats and beatbox that we did earlier?
It's similar in some ways, but we're going to be, here's the key difference. We're going to be differentiating with respect to that variable, not with respect to time. So we're not really interested in rates of change here like we were before. With respect to time, we're interested in knowing how is volume specifically changing with respect to whatever x means. Okay, which in the, we'll define something here. We'll define what x is, right? You get the idea? Okay. So ponder that. Just take a minute or two on your scratch paper and see if you can just think what you can come up with. I want just kind of think about that problem for a second. Okay, and they've given us variables in terms of this drawing. The width and the length of the base are x, and the height is h, right? So just take, literally take a minute and just write down what you can. Just kind of brainstorm for yourself. I'm going to print these out just so I have them available while you're doing that. Okay, so what do you think? So if we've been given this problem without the picture, I mean, what would probably the first thing you'd want to do here be? What do you think?
Volume formula?
Okay, we're going to want volume formula. We definitely, in this case, if it's a geometric thing, make a little sketch, right? Because we want to be able to define some variables, right? So what are the variables here? Well, we've got an open box. So we're defining, in terms of our picture, we're defining x is the width and the length. Let's say the width of the square base. That's all we need, right? Because it's x by x, and we're calling the height h. So those are things we'd want to normally define. How are we going to define the variables that are going to contribute to this quantity that we're trying to maximize or minimize, right? So there's step one is our picture in this case, with the variables defined.
So could we write that as h and x squared?
Well, you can, right, so then step two would be we want to come up with, and this is the key step, and this is the one I think it's really important to always start here, because a lot of times what I've seen with calculus students with a problem like this is we're going to be using some surface area stuff and some volume stuff, right? But it's always a great idea here to just think about what it is you're trying to find and start with that, because that's what we call the primary equation in calculus. So what is it you're trying to optimize? What are you trying to minimize or maximize? What is the quantity? Volume, right? So therefore, we're starting off with our primary equation, which is volume. Okay, what is the volume of a rectangular cylinder with a square base of width x and height h?
X squared times h.
Yeah, is x times h, so x squared times h, right? So step two, if step one is the drawing itself, step two is what we call the primary equation. You don't really need to write this down, because I'm going to give you this in a second. It's the primary equation, and it's just going to be whatever we're trying to maximize. What is it in terms of our defined variables? So x squared h. What's the problem with that? In fact, I need to probably rewrite this, because look, I had it written from before. We talked about how we want it to be a function of a single variable.
That's two variables.
Yeah, look, we got a problem here, right? Volume is a function of two variables, and those are variables, aren't they, right? As I tweak x and h, I'm going to tweak the volume of the box, right? And so we have to do something. We have to somehow fix that. We have to turn this into volume as a function of a single variable, okay? Now, there would be no way to do that if we didn't have some extra information for it. Okay? We're going to need another connection between those variables to be able to relate them in a way where I could write that in terms of a single variable. Think how we do that normally. If we want to eliminate a variable, we have to make a substitution, don't we? Right? See what I'm saying? And so we need to have another equation here, which we'll call a secondary equation Most textbooks would call it a secondary equation. Something stuck with me from college that I really liked is to think of it as an equation of constraint. Because in physics, that's how we talk about it. Yeah.
So, wait.
What do you think it is?
So 108 equals
Good.
x squared plus 4x8.
There you go. Good, good. So the next step is going to be, and this is sort of an optional one, so I'll put an asterisk by it, because you don't need this. If we had stumbled onto a situation in step 2 where we had the primary equation in terms of a single variable, we're good to go. We can just do calculus then. We wouldn't necessarily need that secondary equation. But if we have a situation like this, where our primary equation involves more than one independent variable, then we're going to need a secondary equation for every variable that we're trying to eliminate, right? Now, for us, that's only going to be 2 this year. But in the future, it might be more than 2, right? As you get, like next year. College, you can move further in college calculus classes. So this is our secondary equation. Or, even better, our equation of constraint. Yeah, I like that word because what does it mean to be a constraint?
Limiting factor.
A limiting factor, right? So when we talk about constraints on a system, like in physics, we're talking about what the constraining factors are going to be the things that limit the processor, right? Or limit the physics of a certain situation. And so the same thing applies to math. What's the constraint going to be? Well, you can always bet that there's going to be some numerical, or maybe it's a constant, but something that represents a number that's going to be the constraint. Now, if we didn't have a constraint, the answer would be pretty easy. If I want to maximize volume here, I'm just going to make my box infinitely big. I'm done. Drop the pen, right? But that's not a very interesting problem, right? There are some constraints here. We're constrained by the 108 square inches. So that's got to be the constraining factor. That's got to be the connection that we're going to use to connect X and H in such a way that we could substitute for one and eliminate it, right? So Kirk gave us the secondary equation. It's just going to be the surface area. It's an open box, so we have one base and 4 faces on this, 4 lateral faces on this thing, right? 4 sides that are off the base. So we end up with x squared plus 4xh equals 108. So there's our equation of constraint, right? Which variable, now here's where we want to be smart about this, and we've had a lot of practice that will inform our decision already. Which variable do you suppose we want to eliminate if I look at those 2 equations? Because one of them is very clearly going to be easier to do than the other. But, okay, so we want to solve for which variable to substitute? H, right? How come? Well, look, I've got 1h there, and I've got 1h there. I've got multiple x's in this equation, right? So it'd be much easier to just isolate that h here and substitute there, wouldn't it? Right? Using x would make it pretty difficult. If I got to solve that for x, that's a bad idea. Got a quadratic equation in x, right? So if I solve for h, what do I get down here? I'm gonna subtract that term and divide by 4x. Everybody agree? So I'm going to get 108 minus x squared divided by 4x. So there's my substitution equation. So let's put a box around it, because more than likely we're coming back to that. Oftentimes we're coming back to that. If the question wants to know, like, what are the dimensions? Well, the dimensions are going to be x by h, right? So eventually we're going to have to come back here and figure out what's the value of h. So we'll put a box around it so we can find that equation easily. And then make our substitution, and what do we get? So now we get v equals x squared times h, right? Times 108 minus x squared over 4x. And I could do some algebra on that to make it a little bit easier, right? Like I could, for example, I could cancel an x right away, because that's a factor up there, isn't it? I could cancel like factors. I have a factor x on the bottom, and I have a factor of x squared out front, so that's fair game to cancel an x there. And then if I distribute, let's see, what am I going to get? 108 over 4 is what? 54, so 27. So, is that right? Yeah, 27 over, or x, right? And that first one minus, I'm gonna get an x distributed there, so I'm gonna have an x cubed over 4. Okay, now I could properly write that as v of x, because now it is a function of only x, right? Okay, while we're at it, let's look at the domain. Now, mathematically, what's the domain of that function?
All reals.
All reals, right? But this isn't a math problem. This is a math model of a physical problem, right? So physically, you tell me what's going to be the smallest value of x that I could reasonably consider.
0.
Now, I could consider 0, but is 0 practical? If I were to, and you kind of want to do the cartoon thing in your head here, where you're going to morph this box. Like, would you agree that if the surface area is fixed to be 108, if I make the base smaller, doesn't the thing get taller, right? Because it's got to have a surface area of 108. And so what happens as x approaches 0? What's going to happen to the height if I look at this box? It's got to go to infinity, right? Because the bottom is going to shrink to 0, and so it's going to get infinitely big. And so do we include 0 or not? Honestly, it's up to you. It's obviously not going to be our answer, is it? Right? That's not going to maximize volume, because what would the volume be if x went to 0? Yeah, 0, right? There's no volume contained in there. So your domain, we could either make this a square or a rounded bracket. I'm going to make it a rounded bracket, right? Because we're not obviously going to use 0. It would be impractical, impossible. Is there an upper limit? How big could it be? What do you think? Could x be infinitely big? How come? There is a constraint here, isn't there? Right. What if x can get big to a point, but as x gets big, what happens to h?
Small.
It gets small, right? So as x approaches, as x gets big, it can't really approach infinity, but as x gets big, h is going to shrink to 0. What if h actually became 0, right? If we used all of the cardboard on just the base, so h became 0. Well, we could figure out how big x is, couldn't we? Right? We would know that if h went to 0, we would just end up with x squared equals 108, right? In the limit that, you get what I'm saying? Because there's a physical constraint here, this is actually a physical situation with a area of cardboard that we've got to use. If I let it get so big that the h shrinks to 0, this just degrades into the problem. As h goes to 0, we end up just getting x squared equals 108. And so x would equal mathematically plus or minus the square root of 108, but we don't want the negative one, right? We're talking about a physical dimension. So the square root of 108 would be the biggest possible number that we'd ever consider in our domain. Probably that's not going to be a very good choice, because I'm not going to have any height to my box, so it's going to contain no volume, right? But that's the upper limit of my domain. Somewhere on that domain, and I could have that, so I'll put an open bracket there. Somewhere on that domain, we should probably expect that we're going to get a relative maximum, a peak somewhere that's going to give us our answer. Right? Does that make sense? If we were to evaluate the volume of this thing, where's our volume equation? Right here. I mean, just notice that I want to make this point. V of 0 is 0, right? V of the square root of 108, if I plug that in, I'm not going to do the math here, but what do you think I'm going to get if I plug that in? I'm going to get 0. Yeah. Okay. And I know I have to, because if it's written in terms of two variables up here, when x is 108, we know the value of h is 0, and I would just get the square root of 108 squared is 108 equals 108. That would be a solution, wouldn't it? Right? Okay. So, before we push on with this, I just want you to ponder this for a second. I like to have, this is kind of a big part of becoming a good calculus student. Is this function gonna be continuous? Look at that function on our interval. I mean, it is a polynomial, isn't it? Right? I've got, the coefficient of x cubed is rational, the coefficient of x is rational. Polynomials are continuous everywhere, right? I would never have to pick my pen off the board. So it is continuous. Would you agree that at some point in there, there's gotta be some volume, right? So that's enough to argue right there that there has to be a maximum somewhere between those 2 points, those 2 values of x. Would you agree with that? There has to be some volume, and if it's continuous, there's gonna have to be a highest point in there. Maybe it'll end up being a tie or something crazy like that. I mean, it won't. But there's gotta be at least one, if not more, maxima in that interval, right? Okay? So now we just gotta go find them. Now it becomes a calculus problem, right? We could really, I would say this is where we shift into math mode, and we don't even have to think about the problem anymore. Now we're just gonna engage all the, leverage all that knowledge we've been building by working on calculus all year and learning how to do tables. And so this stuff right here becomes the first line of the problem that we're doing in math mode. So what do we do to make that table? All right, take a derivative. It's an easy derivative, it's a polynomial. What do we get?
X minus 3/4 x squared. 27.
27 minus 3/4 x squared. Okay, so there's our first derivative. Do we want to take a second derivative here? It's a real question. Would you, strategically? I would, for sure. How come? It's easy. It's easy to do. And remember, if we think about tables, and you don't have to. You can do this with the first derivative test. But this, now, we're in math mode. Now we're thinking just in terms of using the tables. We want to work as far down the table as we can, conveniently do, because it's easier to do, right? The second derivative test is easier to apply than the first derivative test. And so if you get just a really simple derivative to take, yeah, take it. Because then you can just use the second derivative test to evaluate all your critical numbers, your interior critical numbers, right? So it does make sense to do. What is the second derivative? Yeah, so -6, so -3/2 x. See, that was worth it, right? To evaluate the sign of a derivative, all we gotta do is plug in a number. Well, what's the sign gonna be everywhere in our domain? The sign, I don't care about the value, positive or negative.
It would be negative.
It can be negative, right? Because our domain they're all positive values. -3/2 times a positive number is negative, so that helped us, right? We know that the concavity of this function is always downward, right? So, makes sense, right? We're gonna get, and we kind of already decided that conceptually, that we know if we were to graph this thing, right? If that's b and that's x, and we're going from 0 up to, the square root of 108. Well, didn't we already establish that the function has a value 0 there and 0 there, but it's continuous, and it's got some volume somewhere on that interval, so it must be doing something like that. It's got to be concave down. How else is it going to have some positive volume between those endpoints and go through those endpoints, right? So, but it's everywhere concave down. Okay, so then all we got to do now is find the critical numbers. So v prime equals 0 when 3/4 x squared equals 27, right? Very good with that? Okay. If I set that equal to 0, I would just add that term to the other side. So all I got to do is multiply by both sides by 4/3, which is going to give me 36. So what's x? I mean, it's plus or minus 6, but of course we don't want the minus because that's not in our domain. right? So we only get one critical number when we make our table. So our domain, we said, went from 0 to the square root of 108. Our one critical number is at 6. 6 is a 0 of the first derivative. It's where our second derivative is negative, right? So what's that look like? A 0 first derivative and a negative second derivative is concave down, so there's our relative maximum, right? So if we just go back here, now if we want to fill in, this is the row 2 in this case. V stands for the function, right? That's volume. So if I just look at this ordered pair, it's telling me that when x is 6, the volume is what? Well, there's our volume function. All we got to do is evaluate that at 6, right? And this is a minor point, but when you're evaluating the function, you absolutely don't want to go back to that formula, right? Because it involves an h. It wouldn't make any sense. We took all that time to build this formula that's a function of a single variable, so use it, right? So we get v of 6 equals 27 times 6 minus 6 cubed over 4. And what's that going to give us? 27 times 6 is going to be, what's it give you? 108. Okay, so we end up with, I'll take your word for it, 108. So the volume is 108, and what would the units be? Good, inches cubed or cubic inches, because we're measuring in inches, right? All our distances and areas are measured in terms of inches. They want to know dimensions, though, so they didn't really ask for the volume. We found it, but what are the dimensions going to be? Well, we know x, which represents the width of the base, is 6. How do I get the height? Good. We got a box substitution equation. We go right back there. And we know that h equals 108 minus 6 squared over 4 times 6. Oh, so what's that going to give me? 108 minus 36 is 72, divided by 24 is 3. Okay, so we end up with dimensions being 6 by 6 by 3, and we're inches, right? Okay, that's going to be that's the box that's going to maximize volume. That's pretty cool. You can do that. You can come up with just using calculus. Okay. So what is that curve actually? We can check this, right? We've got, here's our volume function as a function of a single variable. So if we just take a picture of that, like we could go to Desmos. So v of x equals 27x minus x cubed, 2 minuses there, divided by 4, right? So there's my function, and let's look at our function. We could even choose our, we could choose our window to go from 0 up to square root of 108, right? And so there's our window. Now I want to choose, how about if we choose y to go from, we know the answer is 108. Why don't we just go from like -5 to 115 by 5 or something like that, right? So there's our picture on our domain. That's our volume function. Well, what do you think? If I go in Desmos, what do you know? Okay, there's the maximum at 6. X equals 6. Okay, yes, sir.
Is it just a coincidence they're both one thing? Or is it?
Yes and no. It's 108 would have been from building a million of these kinds of problems. 108 would be a good number to pick because it makes the calculus easy. But in general, yes, it is a coincidence. It's not always going to be that way. Yeah. Okay. All right. So let's just look at. Okay. So you just, take a look at those when you're doing that's the steps we went through, just kind of abbreviated. You like that? Yeah. Okay, so what if we want to do, let's pick a different kind of a problem. So let's do an optimization problem. Let's pick one here. We're not going to get through, I'll be out here in like 5 minutes.
Yep.
Okay, so we won't even really start this, but let's just kind of think, what's our thinking on this? It wants to know which points on the graph of y equals 4 minus x squared, and that's just going to be an upside down parabola with a vertex at 0, 4, right? Are closest to the point 0, 2. Okay, it's kind of a cool problem. So where, like if you were sliding beads, let's say you bent a wire in the shape of this parabola, right? And you set it down on the XY plane, and you're going to slide a bead along this wire. At what points would the bead be closest to the point 0, 2? Okay. So really that gives us, that picture pretty much defines everything, right? We've got x and y are going to be the variables, aren't they? Right? Those are the things that are, that they're going to change as we slide the bead along on the function. Okay? So we'd really start, there's our picture for step 1. We'd start with our primary equation. What is that going to be? What are we trying to minimize here? Closest means smallest, right? Distance. Okay, so we're trying to minimize distance. So that's an S. It's supposed to be an S. So we're going to call distance S. So S, there's one point I want to make here before we go. So S equals the square root of what? If we look at this picture, it's pretty small, but the values of x and y are always, we're comparing the distances away from the point 0, 2. So, like if I were to, let's take this point right here and this point right here, and let's just make that a little bit bigger. Right? So we've got this point, which has definite coordinates 0, 2, and I've got this other point up here on the curve. That's going to have, coordinates x and y, right? They're going to vary. So this represents my distance, S. All this is just, distance formula is just a right triangle relationship, right? So what do we know there? Rather than writing this as a square root, let's just start off with using Pythagorean theorem. And that's how I always, you might remember, that's how I always talk about this. We always talk about it as Pythagorean relationship rather than a distance relationship, because then you don't have to use that darn square root. Right? And then you'll see this will be a good example where you don't want to use it. So what do we get then? What's going to be this change in x? X minus 0. Okay, so that's just going to be x squared, right? How about the change in y?
Y minus 2.
Okay, everybody see that? Okay. Now, I could write this as a distance formula. I could square root both sides if I want to. Let me ask you something. If all we're looking for is what are the values of x and y that are going to minimize distance, do I ever really need to know what that distance is? I really don't. So would it be easier, you tell me, what would be easier to do? Would it be easier to minimize the square of distance or distance? Because aren't I doing the same thing? Distance is a quantity that's always positive, right? Or not negative, I should say. Can't be negative. It can only be 0 or positive, right? So any positive, any non-negative number squared is going to be positive also, right? And so the minimum for distance should also be the minimum for the square of distance, shouldn't it? So this is a super cool trick. We could, instead of calling that s squared, let's just call it something like capital D, right? Which just stands for the square of distance. And we've got some new function that's going to serve our purposes better because it's an easier function to deal with. I don't have to deal with that radical, right? So then we've got D equals this. Okay, but what's the problem with that? 2 variables, right? I got to be able to relate the variables, but that's already done for you, isn't it?
Yeah.
Yeah, right there. Right? It's the equation of the parabola. Okay, we'll finish it tomorrow, but you get the idea? Okay.